Welcome to part 3 of chapter 29. We're going to take a break from lecture and do some examples. So our first example is the force on an electric current in an external magnetic field. We're going to use the equation I just introduced in part 2 of this lecture series. So here we have a wire carrying 30 amps of current. It has a length of 12 centimeters between the pole faces of a magnet. So that's the part that's in the magnetic field. It's at an angle of 60 degrees with this magnetic field. We know that the magnetic field is approximately uniform and has a strength of 0.9 teslas. We're going to ignore the field beyond the pole pieces. What's the magnitude of the force on the wire? Okay, so what are we given? We are given current here with our 30 amps. We are given a length. We're given an angle. And we're given a strength of the magnetic field. And then we are asked to find what is the magnitude of the force. So let's write all of that stuff down. We are given I, that's a big pen. Let's try with a pen. We're given I equals 30 amps. We are given our length equals 12 centimeters. So we could shift that into meters, 0.12 meters. We are given an angle in degrees. And the strength or the magnitude of our magnetic field. So that's in teslas. What we are going to want to do to find the magnitude of the force is we are going to use our equation that just talked about magnitude. So that is I, L, B, and sine of the angle between our current element and our external magnetic field. So we are given all of the things there on the right-hand side of that equation. So to find the magnitude of the force that this wire feels, we're going to have that 30 amps. We're going to have that 12 centimeters that we converted to meters. So I'm going to put a decimal place there, I think. And we have that 0.9 teslas, which is our SI unit, and then sine of 60 degrees. So we're going to check that our calculators are in degrees and not radians. When I put all that information into my calculator, I should get force out in newtons. So when I put that information into my calculator, I get a force equal to 2.8 newtons. Pretty simple to use that, that equation that gives us the magnitude of the force that our current element is going to feel because of an external magnetic field. Now we can also use our right-hand rule to figure out what is the direction, right? So again, remember you take your fingers of your right hand and you point them when they're nice and straight. I'm going to draw a nice little mitten hand. You point them when they are nice and straight in the direction of our current. So I would put my hand like this. Now I'm going to twist my wrist around in such a way that it is going to let my right hand fingers naturally bend in the direction of my magnetic field, right? So going from straight out to being able to naturally bend in the direction of those blue arrows. That is going to let me point my thumb in the direction of the force that our wire is going to feel. And if I look at this, my thumb is going to naturally point into this page, right? So this equation let me figure out the magnitude. This trick with my right hand lets me figure out that this is going to be a force into the page. Right? Now we can see that this force is going to be maximized when the sine is maximized. So the force is going to be maximized when we are at right angles. So when we're going to see the max magnitude of the force when the sine is 90 degrees, when the sine equals 1. All right, so that's one good example. How about another example? Let's say that we have a rectangular loop of wire. It's hanging vertically, and we've got a magnetic field directed horizontally perpendicular to the wire. So remember those dots with a circle around them? That is a magnetic field pointed out towards you. The magnetic field is very nearly uniform, so that's letting us know we can use our equation that I wrote on the previous page along the horizontal portion of the wire from A to B of length 10 centimeters. That length of wire is near the center of a gap of a large magnet producing the field. So that's, again, just letting you know it's uniform. The proportion of the wire loop, not sure why I have this extra word here, the proportion of the wire loop, that should be the top. The top proportion of the wire loop is free from the field, so we see that in the picture. The loop hangs from a balance which measures a downward magnetic force that is over and beyond the gravitational force of 3.8 times 10 to the minus 2 newtons when the wire is carrying a certain current. So we're given current. What is the magnitude of B? Whew, okay, so we are trying to find the magnitude of our magnetic field. We are given current, we are given a force, we are given a length that is within the magnetic field. I think that's it, right? So yet again, we are going to use this kind of thing, right? So we're going to use that equation that tells us about our force. We could write it in terms of magnitudes. I'm not quite sure why my pen is being unhelpful. We could write it in terms of magnitudes and angles between things. Okay, so just like I said in the last slide, we can see that our current, so our current should go across this way. Our current should be perpendicular to the magnetic field the way that everything is drawn right there. And so this sine of theta, that should be a sine of 90 degrees, and that should go to 1. Okay, that simplifies our life quite a bit. So that if we want to find the magnitude of the magnetic field in this very special instance, where that sine is maximized and that sine is 1, we just need to take our force and divide it by our current times that length. Now you may be looking at this picture and asking yourself, what about these side sections right here? All right, so what about those side sections? Well, let's think about it. Using our right-hand rule, if I know on that right side that current is going up and the magnetic field is pointed out of the page towards me, I can figure out with my right-hand rule that my force should be outward. So that outward force is not going to affect this mass balance that is measuring the force over and beyond the gravitational force. And in fact, if everything is nice and even, that force should be counterbalanced by the force on the left-hand side of this loop that is pulling in the opposite way. And because it's an equal length and an equal magnetic field and an equal current, should be an equal force. So all we need to do for our answer to the magnitude of our magnetic field is we need to take our given force, 3.48 times 10 to the minus 2 newtons. So that's in standard units. Our current, 0.245 amps, that's in standard units. And our length, 10 centimeters. Well, we need to change that to meters. And we would get the answer that the magnitude of our magnetic field is about 1.42 Teslas. Easy enough. All right. I put it all on one page, so we don't need this page, but again, you can see that our forces here from the side elements would be out to either side. Practice your right hand rule. Again, put your little right hand mitten with your fingers pointed up along the direction of I in a way that your fingers would naturally bend out of the page in the direction of B, and see which way your thumb points, and see that your thumb matches up. That's my little mitten hand. See that your thumb matches up with the direction of the arrows I've drawn there. All right, so moving on to a slightly more challenging example. Here we have a bent wire. So remember that I said on the previous slide that in cases where our wire is not straight, not always pointed in the same direction in the field, or where our field is not a simple magnitude, we have to use an equation that looks like this. So here we're looking at the current along little sections of wire and how that crosses with the magnetic field. So we can see over here, they've already drawn for us a little segment of wire DL and which direction the force would be due to this magnetic field. So we've got a rigid wire carrying a current I consisting of a semicircle of radius R. So a semicircle is half a circle, and two straight portions shown in the figure over here to the right. Each of those straight portions has a length L that's within the field. So the wire lies in a plane perpendicular to a uniform magnetic field. They tell us to note the choice of X and Y axes. And we want to determine the net force on the wire due to this magnetic field. All right, so what do we need to do? Well, first of all, we need to recognize that we can take this cross product and turn it into a simple multiplication. The reason we can do that is this sentence right here. The wire lies in a plane perpendicular to the field. That is telling us that this sine of the angle equals 1, right? That they are perpendicular to each other. So the cross product turns into simple multiplication. All right, so we have an equation that looks more like this. We have each little bit of force on each little section of wire is going to be due to the current through the wire. It's going to be dependent on the strength of the magnetic field, which they give us as B0. And instead of writing DL, we're going to write RDB. Okay, you'll notice that there's this angle phi that we're going to measure as we go, we sweep across that semicircle, right? So that short length DL we can get from RD phi, as long as phi is in radians. Remember, a circle is 2 pi r, a circle has 2 pi radians, right? So that's a little trick that we can use. We also might want to think about the lengths of wire, but again, just like in the last one, we're going to see that they are equal and opposite forces, so they're not going to contribute. We only need to worry about this semicircular radius, right? So our components are going to cancel. Our x components are going to cancel. You can see that because we have symmetry, we could write a df on this side that matches the df I have circled right here. And the x components are going to be canceling, whereas the y components are going to add together. So our y components remain. And our y components are going to be df and then sine of phi, right? So this little triangle that I have right here, we're going to have to do just df sine phi to get this y component of that little bit of df. Okay. So we're going to put all that together, and we're going to say that our total force that's felt because of the semicircular bit of wire is going to go from 0 to pi radians. That's from 0 right here to pi on the right-hand side. And it's going to be df sine phi, and of course we're integrating over a d phi, right? So if I write that out using the things we've derived on the previous page, we are going through our df, so I b naught r sine phi from above d phi. Okay, so if we do that integral, these first three things are just constants. So we're doing the integral of sine phi. That's going to give us a negative cosine phi. And we're going to evaluate that from 0 to pi. So we've got f I b naught r. We've got a negative cosine phi that we're evaluating from 0 to pi. Then, to do that, cosine of pi is actually going to be equal to 0, and cosine of 0 is equal to 1. That negative sign gives us a doubly negative 1, right? Oh, I misspoke. Cosine of pi is a negative 1, not a 0. Cosine of pi is negative 1, and cosine of 0 is 1. Okay, those negative signs cancel each other out, and we end up with the force being 2 times I times B0 times R, and the direction we saw from the previous page is going to be upward in the positive y direction. Right? Okay, so we'll pause there. We'll pick up with our force on an electric charge moving in a magnetic field in the next part of our lectures.